This is an electron and its wave structure. I will show in this video where it comes from and what are the equations. And I will put $500 of my own money as a cash bounty. We will start from the Einstein equation and construct an electron made of light. Find that the Coulomb field of the electron can be rewritten in a different form. Then we will see the implications of it on bosons and quantum physics. And to put money where my mouth is, here is the cash bounty. I will give $500 of my own money to the first person that explains the value of this constant c. We will see its value in the next slides. The famous Einstein equation E equals m times c squared tells us that the energy of an object is proportional to its mass times speed of light squared. So let's say we have a solid block of mass m. It has an energy just by being, because matter is energy. But why is there speed of light in there? So matter is related to light, but then is matter made of light? Let's construct an electron made of light then. I chose the electron because it seems simpler. But first we have to know what is light. Here is an animation. This is a ray of light or a light wave, and it is characterized by its varying electric and magnetic fields that are perpendicular and that have an amplitude and wavelength. Okay, now that we know what light is, let's construct an electron made of light. We'll start from the wave equation that describes the shape of the electric field. E is the amplitude of the electric field of light, and c is the speed of light. The inverted triangle is the nabla operator. It just means spatial derivative. For example, in one dimension, it becomes this. And we can go further to have an idea of what this equation says. It comes out after not mathematically rigorous calculations that for light equals c times t, which just means that light goes at the speed of light. Okay, seems reasonable. Now we saw that light is oscillating, so we write the electric field in that form. It comes out that the space component of the electric field verifies this simpler equation, the Helmholtz equation, with k defined like this. Remember, we want to organize light in little spheres to form particles. Then it seems natural to work in spherical coordinates, so instead of x, y, and z, we now have r, theta, and phi. We make a new assumption that we can separate space variables. It means that influences of each variable on E is independent. I have a hard time visualizing what it means, so let's keep it there at independent. It comes out 3 differential equations that are solvable and were solved by famous mathematicians, so I'll skip to the solutions. We have for phi a cosine dependency, so its output is between -1 and 1. For theta, we have associated Legendre polynomials. Just remember that its output is between -1 and 1 and that the 0 polynomial is just 1. And finally, the R dependency that looks like this. J and Y are Bessel functions of the first and second kind. We will see later what they look like. In the end, we can form a general solution that is built with a combination of those functions like that. This angular part is just a factor between -1 and 1 depending on the angle we are on the sphere, and this part is a radial oscillation that decreases when you go far from the center. Let's pause a second to see what did we find. We said that if light goes at the speed of light, if it varies in time at angular frequency omega, and if it wants to organize in spheres, it has to do so in a quantized manner. So it relates to the findings of Planck that matter absorbs and emits quantized light. It indeed does, because matter is quantized light, but this it not new. Remember, we want to construct an electron made of light. As a note, this is not completely true considering the spin of the electron, so we assume the electron is not spinning on itself. So this big solution becomes this, and if we use those formulas, we can make it look like this. Just remember this equation because we will talk about it at the end of the video. So we have it now, our electron made of light. Let's visualize what it looks like. So this is 2D cut of an electron to see what's inside. It goes to infinity in 0 and wiggles to 0 when far. But this is only a cut. The full field in 3D looks like this. And you can see the same wiggling outside and going to -infinity in the center. Okay, this is how it looks spatially, but how does it evolve in time? Here's another graph. Imagine a line that cuts the electron. So you recognize the 1 over decrease in amplitude and the cosine wiggling. And when I make time go on, it oscillates like that. We can see that it goes to infinity, and I don't want to check that now because it would take forever. Remember how we said that light goes at the speed of light, so distance equals speed of light times time. Now if we use that, we can rewrite the electron field to something that does not depend on time. Another simplification that we may do is considering that the spatial evolution of the electric field is just light that traveled there from the same source, so it should have the same phase. Let's look at what it looks like. So when I change the phase, it varies like this, and notice that when we get close to pi over 2, it goes to 0 in the center. Okay, we constructed an electron made of light. Let's compare it to what electromagnetism says. Oops, there's a 1 over r discrepancy. What we wrote is actually homogeneous to an electric potential, and we can write it like that if we assume a Lorentz gauge. Then we can derive the electric field from it using this formula. Okay, now it fits. To find the value of our constant c, let's compare it to the Coulomb force. The Coulomb force formula is this. But if we use this formula, we can rewrite it like this. I find it more elegant. Okay, so we have the new electron wave equation, and we define a charge like that. So Lorentz force gives this equation. If we compare it to the Coulomb force, they should have the same amplitude. It gives this equation. Taking the time and spatial averages, we find that our constant c must equal this value so that the two forces match. But what is this value? I don't know. If c equals 1, it means there is a perfect match and our new formula is complete. So this is the value of c we find in the normal picture. But if we tweak a bit some values as seen in the literature, or if we use the spatial electron we saw before, we find slightly different values, still not 1. Now instead of defining a new charge, one could imagine defining a new force equation given by the square of the electric potential. Adding a bit of physical interpretation, we can find a slightly different value for our constant c, still not close to 1. Now let's compare the case when both electrons do not have the same temporal phase. The average force looks something like that, and it depends on the phase shift between the two electrons. If there is no phase shift, the force is positive, so repulsive, and we interpret that as 2 electrons. If there is a pi/2 phase shift, it means there is no interaction between the two particles, they are bosons, etc. So what happens when we take 3 electrons with different phases? What happens is the nature of the electron is defined by the phase point of view. But this raises more questions. What about phase values in between? If you have answers, please comment or link another video or article. I'm interested. Okay, let's go further and find the force if we have 2 such particles, this time of different masses, meaning different k. The general force averaged in time looks like that, and we can find that the first term has a spatial average of 0, except when k1 equals k2. The force diverges when r tends to 0, except when phi r1 equals phi r2 equals plus or minus pi/2. So on average, particles only interact if they have the same k, or if they are really close. Now if we use this k-mass relationship, we can reformulate the force in this general force. Making more assumptions to simplify it, we find those formulas. If we continue on that right path, we have this. Looks close to gravitation? No. Here's the gravitation formula. If we define our force using 2 effective masses, we find this formula. Okay, I agree, I forced my way into it. But what this means is that if particle 1 is the sun and particle 2 is the earth, this would say that the effective mass of the sun is larger than the effective mass of the earth as we know it, but actually its true mass is smaller than the earth's true mass. But this is for r really small, and I speculate that at planet scale, r is more on the order of magnitude of 1/k, if that even means something. This comparison is highly speculative and should be taken with a lot of grains of salt. And we did not discuss about higher orders of the general solution. What do they look like? Like this, and we can see that they behave radially the same when r is far superior to 1/k. Remember, I told you to remember one equation. No worries, I copied it just there. It means that for the potential, and actually the same applies to the electrical field, solutions can have sine and cosine forms. However, there is one big difference between the two, how they behave when r tends to 0. Here is a graph of both functions to see what happens. The k times r comes out of the sine when r tends to 0, and the potential takes a finite value, whereas for the cosine it diverges to the infinity. Now quantum physics generally gets rid of the infinite value, invoking the normalization of the wave function argument. But the wave function is the electric potential, so the renormalization actually means the integral of the force should be finite. It seems reasonable. Now electromagnetism says that yes, the electron field goes to infinity, and that's okay. Experiments will tell us which one is right, but until then I prefer the quantum physics version. So we've seen the new rewritten electron-electric field and what are its implications. Remember, I will give $500 of my own money to the first person that explains the value of this constant c. The winner, if winner there is, will be announced on this channel. If you believe you found it, give your solution in a comment under this video. I already checked combinations of 2, 3, and pi at different powers, and it does not fit. Disclaimer, it may be only the angle that I presented and nothing else. As weird as this would be, then the prize money will not be distributed unless you can explain it. I will also not accept random rationals unless you give a reason for where the values come from. The thing is, I don't know, and that's why I put a prize money on it. If you liked the video, like, comment, subscribe, and share it with friends.